See, let's do some methods of preparation of amino acids. One very well-known method that is known as Stricker synthesis. So, Stricker synthesis. So, see, in this synthesis, we take aldehyde, RCOH. All of you are knowing all these reactions. RCHO plus you can take ammonium chloride, or you can take ammonia basically, or you can take primary amine. So I am taking here R dash CH2 NH2, or you can take here in place of this ammonia, and source of this ammonia is basically ammonium chloride, right? That will give a good yield, right? So all of you are knowing that this is a nucleophilic addition reaction, which is the characteristic reaction of this carbonyl compounds. So this is electrophile, so this will attack like this, and this will go like this. So you will get R H O minus N H H CH2R plus. So there is a acid base reaction. This H will go here, OH, and H, CH2R, right? So this you will get, and all of you are knowing that at the same carbon, if two OH groups are there, so elimination of water will take place. So this OH and NH2, if NH are there, then also elimination of water, because poor base is a better leaving group. So if there is a choice between water and ammonia, so obviously water will eliminate. So dehydration will take place, right? So you will get C here, double bond, N, CH2, and R and H. So all of you are well aware of such type of reactions. Already, gone through in the reactions of carbonyl compound, right? Now, with this material, C double bond N CH2R R and H. Now you can take KCN or NaCN, means Cn minus, a nucleophile, right? The source of this Cn minus is KCN or NaCN, you can take, okay? Now see, this is a nucleophile, so again electrophilic center is this, so this Cn will attack here. So this will move like this. This is R dash basically. So what we will get, R H C N N, and H from aqueous medium it will take NH CH2 R dash. Now hydrolyze this, make the hydrolysis. So you will get COOH RH NH CH2 R dash, right? So this is the general reaction. When you take this ammonia in place of this, so you will get here NH2, right? So I have written first this general reaction, familiar reaction to yourself. Now we you can, this is alpha amino acid, right? See, this is alpha carbon, amino group is there. So when you take suppose that if you take CH3COH, CH3COH, and you take ammonia, oh, excuse me, ammonia plus NaCN, so you will get CH3 CN H NH2, right? When you take here ammonia or ammonium chloride also you can take NH4Cl. So this is I mean general reaction of Stricker synthesis I have written here in terms of RCH2NH2. Now I am taking this ammonia or ammonium chloride NaCN. So your this compound, and after that hydrolysis. So Stricker synthesis in one step also you can show like this. So COOH NH2 CH3 and H, and you know this is alanine, alanine, right? So in this way you can I mean prepare alpha amino acids, alpha amino acids, right? Okay, good. So this is Stricker's synthesis. Second method, you can take general, not any name reaction. You can take alpha halo acid, alpha halo acid. How to prepare this alpha halo acid? You can prepare alpha chloro, alpha bromo in alpha chloro or alpha bromo acid, right? By HVZ reaction. By first prepare alpha halo acid by HVZ reaction. Hell Volhard VOLHARD Zelinsky ZELENISISIKY. Hell Volhard Zelinsky reaction, right? So if you prepare alpha halo acid, and this method is a good method to prepare alpha halo acids, right? So alpha halo acid, if you take carboxylic acid CH2COOH plus Br2 plus PBr3. PBr3 is catalyst here, right? So you will get R CH Br COH, right? Similarly, if you take RCH2COOH and Cl2. Here, if you take Cl2 plus PBr3, right? Catalyst is PBr3 catalyst. So don't confuse that this bromine is coming from this PBr3. No, not right. So you will get R CHCl COH, right? So you can prepare alpha halo acid. Now react this alpha halo acid RCHX COH plus ammonia. So you will get alpha amino acid RCH NH2 COH alpha amino acid, right? So this is the second method. So this HVZ reaction, for this HVZ reaction, what conditions should be there? Carboxylic acids, whatsoever you have taken, that must have alpha hydrogen. So the necessary condition for HVZ reaction, that this carboxylic acid must have alpha hydrogen, right? So this alpha hydrogen, this will replace with halogen, and you will get alpha halo acid, and this halogen can be replaced by this ammonia. So you get alpha amino acid. And now see a very popular method of preparation of alpha amino acid is the Bucherer-Berg synthesis. So Bucherer So see, this is a very this method involves a very long, steps. But I'm not going to write all those steps. Here I'm simply writing the condensed part. Although this is not, I think it is not mentioned in your syllabus, but this is very popular synthesis. RCO R dash. You can take ketone and KCl ammonium carbonate, second ETOH, and water. So you will get a cyclic compound, and this cyclic compound is very popular cyclic compound. Multi-step reaction involves here, right? So this is Hayden twine. Hayden twine. This compound is known as Hayden twine, and on hydrolysis, when you hydrolyze this, you will get alpha amino acid. This so this NH2 group is here and carboxylic group is here like this. So you will get C NH2 R dash C O OH, right? Alpha amino acid. So variety of alpha amino acids can be prepared by this method, but I am not writing here the detailed mechanism, right? So these are the methods of preparation of alpha amino acids. Now see the properties. Properties. So first I am taking heating effect. Heating effect. So when you heat this alpha amino acids, so two molecules condensed with each other and they produces this a cyclic compound known as diketopiperazine. Right? So OH and H and OH and H. So you will get NH. Right? This compound is known as diketopiperazine. Diketopiperazine. Okay. So if you see, this is very symmetrical molecule, and this has the center of symmetry. Opposite groups are equidistant. All this, right? So this is at point of symmetry. Now, other reactions, all of you are knowing that it has NH2 group as well as COH group. So some of the reactions you have already gone through with respect to the NH2 group, and some of the reactions with respect to the carboxylic group, right? So general reactions, we can say if we take R, CH2, NH2, COH, right? So suppose that if you heat this with the HNO2 or NaNO2 diazotization reaction, NaNO2 and HCl 0 to 5 degrees Celsius. If you heat this compound, so you will get this NH2 into OH. So R CHOH COH alpha hydroxy acid, and this reaction is called diazotization reaction. Already we have discussed this in the reaction of this NH2 group. Remember. Now, esterification. Suppose that if you take methyl alcohol and H plus, so this carboxylic group is involved here. So what we get are CH2, NH2. Medium is acidic, so here we can write NH3 plus COOCH3. right? Suppose that if you take CH3COCl acetylation reaction in pyridine. So all of you are knowing that the acetylation reaction, it is the characteristic reaction of NH2 group. So, and this reaction is the characteristic reaction of COH. So COH group is involved here. Now NH2 group will acetylated. So what we get are C, not CH2, this is CH, right? Okay. So R, CH, NH, CO, CH3, OH, right? So this is acetylated derivative of this alpha amino acid. So these are the, some general reactions. Similarly, if you take R, CH, NH2, COOH, lithium aluminum hydride, if you take lithium aluminum hydride first, and second this hydrolysis, so you will get what this COH group will reduce into CH2OH, so you will get RCH and CH2OH, right? So if you reduce this with lithium aluminum hydride, so you will get what this COH group will reduce into CH2OH with lithium aluminum hydride, right? Similarly, reaction with copper. So basically, this acts as a ligand. So when you take this RCH in coordination chemistry, you will see that this alpha amino acid molecules, they are acting as a bidentate unsymmetrical ligand. So with transition metals like copper 2 plus, iron, nickel, so all they form such type of complexes. So Cu2 plus and C, COOH, RH. R, right? So this is what, this is complex, right? So coordination number 4 for this complex, copper 2 plus is the central. This will donate one lone pair, this will donate one lone pair, oxygen will donate one lone pair, and this oxygen will donate one lone pair. So coordination number is 4 for this complex. Okay. So this is like other metals like copper, if you take other transition metals, so you will get similar kinds of what this complexes, right? Now see one very important property, and all of you should be ready for such type of questions in your IIT JEE advanced exam. See, if you take glycine CH2 NH2 and COOH. So this has, basic group as well as acidic group. So this is what basic. This is what acidic group. So and pH close to 6. Aqueous solution, if you take up this, so pH is close to 6 to 7. So when this, if you examine this, so it is almost neutral, you can say, neutral, and very weak acid, we can say, very weak acid. And we won't get any sharp endpoint when we titrate this glycine with NaOH. See, this is the second example of your chemistry where when you titrate this compound, similar compound like H3BO3. The first example in your syllabus, that is H3BO3. This is very popular, and usually, this compound is given. Usually we give this reaction and practical. Question in the practical exam. H3BO3. This is also a very weak acid. Very weak acid. And when you titrate this with NaOH by using phenolphthalein indicator, no sharp endpoint. No sharp endpoint. So what we do for this, we just put some organic compound here, like glycol, 1,2-diol. So if such type of compound we can put here a small quantity in the this titration, so we will get a sharp endpoint and we can quantitatively estimate H3BO3 from any sample. So this is one case where we are titrating a weak acid in presence of some compound which make its make it strong, so that we can titrate and quantitatively estimate, right? So this is the purpose basically, that we cannot quantitatively estimate H3BO3 directly if you titrate this with NaOH by using phenolphthalein as an indicator. But if you take this H3BO3 with some certain compounds, not specifically that you can take, always take ethylene glycol, you can take catechol, you can take some other compound, some benzene ring, and but two OH groups should be adjacent positions should be there. So if you take such type of compound, this will make it a strong acid, and we can titrate this very easily and we can detect the end point. Got it? Similar case is here. This also we cannot titrate this with NaOH. We won't get the sharp endpoint with this glycine in the acid-base titration. So no sharp endpoint, no sharp endpoint, endpoint in acid-base titration. Acid-base titration. So there is a difficulty to estimate this compound quantitatively, right? So what we can do? We can take formaldehyde, like here we are taking 1,2-diol. So here we are taking formaldehyde, C double bond O, formaldehyde. Treat this compound with this alpha amino acid. So NH2 group will react. So water will eliminate, and you get C double bond N, CH2, and now this time your this I mean compound can be titrated. Now this is a much stronger acid than this, and how this acidic strength will increase here? See, the conjugate base is here. This is the conjugate base, and this group acts as a electron withdrawing group here, right? So now this can be titrated, can be titrated against NaOH, right? Can be titrated against NaOH. Okay. So in this way, you can, I mean, quantitatively estimate this compound, because 1:1 molar ratio is there. So if you calculate the moles of this present in the system, so you can indirectly estimate the quantity of this. So this is the second case. Now, see, another and very important reaction of this amino acids is condensation. Condensation, right? So condensation, two or more alpha amino acid molecules, they are condensed with each other, and they form the amide linkage. And basically this is the, I mean, one step of the preparation of protein, right? So see, NH2 and COH group are condensed. So this is COH plus NH2 CHR COH. So see this OH and NH2, this will condense in presence of H plus. H2O will eliminate. So we will get NH2 CHR CO NH CHR COH, right? COH. So this is what, see, this is the amide amide functional group. Now one more possibility is there. One more possibility is there, that COOH of this first, COOH of this, no, NH2 of this, not COH. NH2 of this, and so this can be also condensed minus H2O, right? But remember one point, that in nature, see, nature, creation of nature is so selective, and reactions what occurring in the nature, they are so selective, so perfect, that humans cannot do that. All natural amino acids, I mean, this is dipeptide. Similarly, three units will combine tripeptide, tetra, and polypeptide up to the 100 amino acids, and even protein. each and every sequence is so systematic in the nature that there is no variation. And if there is a variation in the sequence of amino acid, there is a serious problem with the humans. Some genetic diseases are related to this. Change in the sequence of this amino acid. So remember, dear students, there is no such condensation in any natural polypeptide, not found in natural polypeptides. Means if you have three amino acids, let A, B, and C. Suppose that these three amino acids are given to you, and it is asked, okay, synthesize, the tripeptide. I'm not telling that laboratory it is not possible. In laboratory, everything is possible. But in nature, this is not possible. So suppose that sequence of amino acid is given like this: A, B, and C, and CBA. Suppose that this two sequence it is given. I have just reflected this C here. Means if you reflect this molecule like this, so you can achieve this. So these are the three amino acids. I'm taking one example and trying to explain what is the difference. So this is three amino acids, three amino acids, A, B, and C. This is one sequence. Other sequences are also possible. BAC is also possible. All the other are possible. I think this is factorial 3 tripeptides are possible here. Factorial 3 total tripeptides. 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 Right? So factorial 3 tripeptides are possible. I am taking these two examples to explain you this difference. So if this tripeptide is there, means this COOH of this is free, and NH2 of A is free. This is very important chemistry. You know, sometimes if examiner will give you the tripeptide in the general code word and ask, okay, hydrolyze this. So which NH2 of which is where and COH of which is here, it makes the difference. So here COH of this is free, A is free, and here NH2 of C is free. So if you see carefully, these two are different, not the same. Different sequence. Different sequence, right? So this is very important point. So if you have three different amino acids A, B, and C, and if you want to prepare tripeptide by using all three, then the total number of tripeptides, total tripeptides peptides is equal to factorial 3. So this is equal to 3 into 2 into 1. So total 6 tripeptides are possible, right? One more combination is there. Suppose that you have this three uh, amino acids, A, B, and C, A, B, and C, and you want to prepare tripeptide, tripeptide by using anyone, not necessarily that all three should be present. So A may be present, B may be present, C may be present. So in this situation, total number of tripeptides, total number of tripeptides is equal to 3 to the power 3. So you can make the formula now. All of you are knowing this, permutation combination. So total, you may have 3 to the power 3, mm, possibilities. So 3 into 3 into 3, so 27. So 27 different, tripeptides can be prepared, right? By only, you can take only A, only B, only C, then A and B, then B and C, A and C, and different sequence, like this. So you will get total 27, correct? So this is, properties, chemical properties of this, and this is most important reaction is this condensation, most important reaction, because this is the basic reaction of protein synthesis. Whether you are synthesizing in laboratory or you are synthesizing in, it means this is synthesized in our body, this is the basic reaction, condensation reaction, right? And in human body, when protein is synthesized, see, there is a very, selective reaction that COH of this will condense with this. Although humans are very clever, and now they have devised the mechanism to synthesize the polypeptide chain, like insulin. All of you are knowing insulin, hormone, proteinous hormone, in which amino acids are there. So now humans are preparing that amino acid, and in the same sequence as natural insulin is there, right? So we have method, but not in your syllabus, to how to devise this synthesis of polypeptides in a directed manner, right? Okay. Now some physical properties are left, so let's see some physical properties. Well, see, physical properties. So it is, polar groups are there, NH2 group is there, COH group is there. So alpha amino acids are have high dipole moment, have high dipole moment. Second property, forms Jupiter ion, forms Jupiter ion, Jupiter ion at particular pH. Not at every situation they form this Jupiter ion. Jupiter ion means dipolar ion, basically. Means positive and negative, both poles are present in the same molecule. So dipolar ion, dipolar ion, right? So this is Jupiter ion. They form Jupiter ion. See how, suppose that if you have this CH2 COOH and NH2. Suppose that this compound you have taken at some solution at pH, let it be pH is equal to 1, at pH 1. So pH 1 means strongly acidic medium. So if you have taken this glycine molecule and alpha amino acid in the acidic solution, acidic medium, so this is a basic group. So this will protonate at this pH. Obviously, this will protonate. H plus will go to combine, and this will form NH3 plus CH2 COOH. This is not a Jupiter ion. This is a single ion, positive ion. This is cation basically. This is cation. When you take this molecule in pH 12, suppose that basic medium. So if you take this molecule in basic medium, so what will happen? This acidic hydrogen will lose in this basic medium. So this will exist as a NH2 CH2 COO minus. This will exist as an anion, not a Jupiter ion. But if you take this molecule at pH 6 to 7, 6 to 7, then what will happen? This molecule exists as a NH3 plus CH2 COO minus. I am not telling that 100% will exist in this form, but major portion will exist in this form, right? And we can find out at what pH this will exist 100%. We can calculate, right? So see here, this is anion, this is cation on the same molecule. So such type of ions are said to be Jupiter ion. Jupiter ion. So alpha amino acids, they form Jupiter ion. And one property is related to this, that is known as isoelectric point, right? So third property is isoelectric point. Isoelectric point or isoionic point. Isoionic point, right? So it is defined at the it is abbreviated as a PI. So it is defined at the pH of aqueous solution. pH of aqueous solution. Aqueous solution at which alpha amino acid molecule exists as a dipolar ion, exists as a dipolar ion, right? That is, or you can say that is, migration is stopped. Migration is stopped between electrodes. Right? So migration is stopped between the electrodes. Means if you take aqueous solution and suppose that this Jupiter ion exists like this. You have electrodes, positive, negative. So if this molecule, exists as a Jupiter ion at a specific pH, as I have shown here, so at that pH, this migration of this, dipolar ion is stopped between the electrodes. So that pH is known as the pH at which the migration is stopped. That is known as isoelectric point. Isoelectric